Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll start a new topic called work. You've probably heard the term work before in your daily lives, but in physics it has a very specific quantitative meaning. So let's get into it. The differential amount of work done, differential just means a small amount of work done, because we first define work over very small intervals and then we add it up to get the total work. So a very small amount of work done is equal to the force applied on an object having a dot product with the differential displacement. So if I have an object and let's say I apply a force F1, let's say I apply another force F2, and let's say this object moves slightly in this direction. So the displacement vector, we label it as dr. These two are vectors as well, so I'll put an arrow over them. Dr is nothing but it is dx I cap plus dy j cap plus dz k cap. That is, dx is the small change in x, dy is the small change in y, and dz is the small change in z. And if you take these three and add them up according to their unit vectors in the x, y and z direction, you'll get the displacement vector dr. It is just the change in displacement of the point of an object, right? And so the work done by the force F1 will be F1 dot dr, and the work done by the force F2 will be F2 dot dr, right? So there are many specific cases which you'll see again and again in which these formulas end up becoming simplified. So let's look at some of those. The first case we'll look at is the case of a constant force. This is the most familiar one and you'll see this most often. Constant force. Now we know that force is a vector, so constant force has a special meaning. It means the force should be constant in both magnitude and direction. Right? So if the force is constant, then dW, a small amount of work done, will be F. Let's calculate the work done by a particular force F dot dr. By the way, dot product is also called the scalar product as the resultant is a scalar. So this definition of work implies that work is a scalar quantity. It has only magnitude, no direction. Now this is a small amount of work done. Let's say an object goes from point A to point B. Right, it might go through a random path, and if we divide it into many small intervals, and between any two intervals the displacement is dr. And let's say there is a constant force acting in this direction. So from this point to this point we take the vector dr, which is the displacement, which is this vector, the position vector of this point minus the position vector of this point. We've seen that stuff in vectors already. And if we take the dot product of dr with the force, it will give us the work done in taking the object from point 1 to 2. Similarly, if we take these two events and we take f dot dr, it will give us the work done between the points 2 and 3, and so on. Now since work done is a scalar quantity, it has no direction and we can add it according to the normal rules of scalar addition. For example, 3 kg plus 5 kg is always 8 kg. Similarly, work can be added up. So when we add both sides, since these are differential amounts, not finite sized amounts, instead of sum, we are going to have to do an integral. So let me integrate both sides. Integral of dw will be w, which will give me the work done. And let's say I go from the point R1 to the point R2. That is the point A. If you don't remember it, let me make it a little bit more clear. We draw some origin and we draw some axis, and this position vector of this point will be called R1 or RA, whatever you want to call it, and this will be called R2. And the difference between the position vectors, the final position vector minus the initial position vector, will be this vector, which will be the net displacement. So W will be equal to, now since F is constant in both magnitude and direction, I can take this outside the integral. So it will give me F dot integral of R1 to R2 dr. right? Now dr is these small series of vectors, and if you add them you will get this final vector, right? And this vector is r2 minus r1, or you can see it even more mathematically. Integral of dr will be r. You've not exactly seen vector integrations right now, nor will you really see it later on, but for the purpose of this discussion you need to know that for most cases vector integration is like scalar integration. So dr integral will be r going from r2 to r1, so it will give me f dot r2 minus r1. If I want to label this vector as d, I can write it as f dot d, which I can also write as f d, where these are the magnitudes now because I don't have an arrow in front of them, cos theta, theta being the angle between the force and the displacement. This is a formula which I am sure you've seen in previous classes. Work is the force multiplied by displacement multiplied by the cosine of the angle between them. But this is a special case of the more general case, which is the infinitesimal amount of work done in moving an object from through a displacement dr by a force f is f dot dr, and if you add them up for a constant force you get w is equal to f d cos theta, right? Let's take a small example of this. So let's say I have a cliff, and from the top of a cliff I throw an object and it goes like this and it falls down, right? So let's call this the x-axis as usual, and this is the y-axis, and this is the origin. So the force in this case is only due to gravity, so it will be mg, and the direction will be negative, so it will be minus mg j cap, right? The displacement at any point will be, this is the standard definition of displacement, dr is dx I cap plus dy j cap plus if needed dz k cap, but we are just talking about 2 dimensions right now. So f dot dr will be minus mg dy, and this will be dw, and if you integrate it you will get w is equal to minus mg y, where y will be the change in displacement. It should rather be minus mg y2 minus y1, or it can also be mg y1 minus y2, right? So this is the net work done by the force of gravity. We see that we take the displacement net is in this direction, by the way, right? So if this height is y1 initially, finally we are at y2, we see that y1 is greater than y2, so the work done is positive. But we could have also used this formula directly, which would have given me, this is the displacement, if this is y and this is x, then this is root x square plus y square, and this mg is the force. So we take the force dot the displacement dot the cos theta, and displacement cos theta will again give me y. So we see that in both cases the answer is the same, and also we see that the work done by the force of gravity does not really depend on the intermediate path, right? If I throw it in some other way, such that is also ends up at this point, or it ends up at the same vertical height, the work done by the gravity will be the same, right? So the work done by gravity only depends on the initial and final point, not on the path taken between the points. Remember this will be important in the next lecture when we talk about different types of forces, right? Let's take the second case. This was for constant force, remember, constant magnitude and direction. Gravity is a classic example of this type of force. Another type of situation could be in which the force is perpendicular to the displacement or the velocity. For example, we've seen pendulums earlier in dynamics of circular motion. So if this is a pendulum and it's moving in this direction to and fro between these 2 points, and we take a random point in between. The total would be theta naught and this would be theta. There is one force acting, which is the force of gravity, which is a force which is constant. We've already seen that. Another force acting would be the force of tension. That force is acting towards the center along the direction of the rope. And this is the displacement dr. The next instant the particle will be here, the next instant here. So dr has a direction which is tangential. T has a direction which is radial. We know that the radius is perpendicular to the tangent. That's basic geometry, right? So we know that for all instants of time, T is going to be perpendicular to the displacement vector, or is going to be perpendicular to dr by dt as well, which will be the velocity vector, right? So in small differential cases, dv is dr by dt, so dv and dr have the same direction, right? Which means that T dot dr will be 0, right? Which means that sum or integral of T dot dr will be 0, which means that the work done will be 0. So when the force is perpendicular to the displacement, there is no work done. And the classic example of this is whenever you tie an object to a rope and move it around, even in a vertical circle. If you move an object in a vertical circle by tying it to a rope, the force due to the rope will always be perpendicular to the direction, hence it will be perpendicular to the velocity, and hence it will never do any work, right? So let's combine these two into a problem. I have an inclined plane, but it's not really an inclined plane because it's not really a plane, it has a very rough structure, but we are given that all throughout it is smooth. Smooth means that it's frictionless. The coefficient of friction is 0, right? Let's take this total height to be y0. We drop an object of mass m, we just release it from this point and it starts moving down. We want to find out what is the total work done on this object. If this is point A, what is the total work done on this object by the time it reaches point B, right? So we want the total work done. Now total work done will be the sum of the work done by the individual forces, right? So it will be integral of F1 dot dr plus integral of F2 dot dr plus dot 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 if there are many forces F1, F2, F3 acting on a particle, right? But dr is common in all of them, so I can take it outside, and this is also equal to integral of F1 plus F2 plus dot dr, right? This is the dot product, but that is equal to the integral of F resultant dot dr. We know what the resultant force is. If we add up all the forces acting on a particle, it will give me the resultant forces. The resultant force is the mass times the acceleration, right? Remember, the individual forces are not equal to mass times acceleration. The net force acting on a particle equals the mass times acceleration. That's a version of Newton's second law, right? So this shows us an important result, that to calculate the work done on an object, we can either calculate the work done by the resultant force, or we can calculate the work done by individual forces and add them up, right? In this case, we'll use the first way. So what are the forces acting on this object? There are only two forces acting on this object. There is the force of gravity, mg, acting downwards, and there is a normal force which always acts perpendicular to the plane. Here the normal force will be in this direction, here it will be in this direction, here it will be in this direction, this direction. Remember, the normal means perpendicular, so the normal force is the force which is perpendicular to the plane at all times, right? And there is no frictional force because we are given that it's smooth, right? So the work done by gravity will be, the displacement is in the downward direction, remember, right? So the displacement is y0 in the downward direction. The force is mg in the downward direction. The angle between them two is 0 degrees. So the work done by gravity will be equal to mg y0. Positive because the direction of the force and the direction of displacement are the same, right? The work done by the normal force will be 0 because this falls into our first category of constant forces, and this falls into our second category of forces which are always perpendicular to the displacement. The displacement will always be along the surface, and the normal force will always be perpendicular to the surface. So the angle between them will always be 90 degrees. So the net work done on this object is equal to mgy. Right? Let's take the third and final case, that is spring forces. We've seen spring forces before, but I'll do a small recap of them. These are my fixed walls. There is a spring which I have attached, and there is an object. Let's call this length to be capital L. This is called the natural length of the spring. It is the length which a spring has if you just leave it on the table and don't apply any force to it. If you want to extend the spring, that is increase its natural length, you will have to apply a force. If you want to compress a spring, that is decrease its natural length, then also you would have to apply a force. And the force which you apply would be the same as the force which you apply on the spring by Newton's third law would be the same as the force which the spring applies on you, and its definition is, this is called Hooke's law, it is minus kx. Minus because it is opposite to the direction of displacement. If I push, the force by the spring will be such as to oppose the force by my hand. If I pull, the force when again will be opposite to me. And a nice way to remember this is that the direction of force is always such that it tries to regain its natural length. So if I apply a force towards the right, it will apply a force towards the left, and if I apply a force towards the left, it will apply a force towards the right. The second important thing, this x, sometimes students get confused and assume this to be the length of the spring. This is not the length of the spring, because that would imply that even when the spring is at its natural length, it has a force equal to minus FKL, which is not true. This x is the extension or compression of the spring. That is the change in its spring from its natural length. So if this is L and I extend the spring a little bit and make its new length equal to L1, then x magnitude will be equal to L1 minus L, not L1 and not L. Okay, so let's say the spring is initially at an extension x1, and finally I apply an even greater force towards the right and make it an extension x2. What is the total work done in this case? So the differential amount of work done will be f dot dx, which will be minus kx dx, right? Because f is minus kx. So now I went to integrate it, but remember in this case the force is not constant. In fact, this x will stay inside the integral. So if I integrate it, I will get work done will be equal to integral of minus kx dx, where the extension goes from x1 to x2. So it will give me half k x1 squared minus half k x2 squared, right? Or if the initial natural length was 0, then x1 would be 0, then it would give me minus half k x2 squared, all minus half k x squared. This is if it is at natural length initially. So just what you need to know is the work done by the spring is half kx1 square minus half kx2 square. Now I'll give you a trick to remember this. Half kx square is easy to remember because kx dx has an integral of x dx has an integral of x squared by 2, right? The sign is something in which most students get confused sometimes. So a nice way to remember the sign is the standard way. If the force is in the direction of the displacement, the work is positive, else the work is negative. So for example, if the spring is at its natural length and I apply a force towards the right to extend it, then the displacement of the block is towards the right, but the force applied by the spring is towards the left. So work done by the spring will be negative. Now if I apply a force towards the right and extend it and then release it, that is I am no more applying any force, then the block will start moving towards the left due to the force of the spring which is towards the left. So in that case x2 will be 0 and final length will be 0 and x1 will be something and work done will be positive. Similarly, if I am compressing, then the work done by the spring is negative. However, once I've compressed and released and the block is moving towards the right, the work done by spring will be positive. Right? So you've seen three categories: constant forces, forces which are always perpendicular to displacement, and variable forces. Variable forces in this specific case of spring forces, right? In most cases, one of these three will be the category into which your forces fall, and you'll be able to use work done to calculate a lot of other results. Just one small result I'll tell you right now. We'll see this again afterwards. The work done is, right now I'm just going to take one dimension, right? So I'll write it as f dx. That can also be written as ma dx. The generalization to 3 dimensions with vectors is easy enough. You can try it on your own, right? But we saw 3 formulas of acceleration. Acceleration was dv by dt, or it was double derivative of x. But another formula was v dv by dx. And we get it because if we write dv as dx by dt, dx and dx will cancel and we'll get dv by dt. So I'm going to use this third formula here to substitute a. So this gives me mv dv by dx dx. Now dx and dx cancel and I'm left with mv dv. I apologize, this should be the differential work done. Right, so differential work done is f dx, which if you manipulate it enough comes out to be mv dv. You can integrate both sides, and if the initial speed is v1 and final speed is v2, you can see that the work done will be half m v2 squared minus half m v1 squared. This is a very important result called the work energy theorem. And what it says is the work done equals the change in kinetic energy. Kinetic energy, I'm sure you've seen the term before, but if you've not, kinetic energy of an object, I'll just write Ke, has the formula equal to half mv squared, and it is the energy of an object by virtue of its motion. Right? So the change in kinetic energy, that is the final kinetic energy minus the initial kinetic energy, will be equal to the work done. This is the work energy theorem. We'll see this in more details in next lectures, but one thing I want to make sure you understand, because we'll expand on this further. Everything we've talked about till now, we've talked about a single particle. Or another thing would be rigid bodies, which fall sometimes in the category of single particles, but we do not deal with that right now. A single particle means there are no internal forces. Right? So, for example, if I just leave two objects under their mutual gravitational attraction, they'll start moving towards each other. Right? I cannot apply the work energy theorem as it stands in this case to this complete system. Right? We'll be able to do it later on by defining potential energy. Right now, everything I've told you, work energy theorem and ways to calculate work, applies for a single particle. Right? So in next time, we'll see potential energy and we'll see how to extend this to multiple particles. Thank you.